Combinatory logic is a notation to eliminate the need for quantified variables in mathematical logic. It was introduced by Moses Schönfinkel and Haskell Curry, and has more recently been used in computer science as a theoretical model of computation and also as a basis for the design of functional programming languages. It is based on combinators. A combinator is a higher-order function that uses only function application and earlier defined combinators to define a result from its arguments. Combinatory logic in mathematics. Combinatory logic was originally intended as a pre-logic that would clarify the role of quantified variables in logic, essentially by eliminating them. Another way of eliminating quantified variables is Quine's predicate functor logic. While the expressive power of combinatory logic typically exceeds that of first-order logic, the expressive power of predicate functor logic is identical to that of first-order logic. The original inventor of combinatory logic, Moses Schönfinkel, published nothing on combinatory logic after his original 1924 paper. Haskell Curry rediscovered the combinators while working as an instructor at Princeton University in late 1927. In the latter 1930s, Alonzo Church and his students at Princeton invented a rival formalism for functional abstraction, the Lambda calculus, which proved more popular than combinatory logic. The upshot of these historical contingencies was that until theoretical computer science began taking an interest in combinatory logic in the 1960s and 1970s, nearly all work on the subject was by Haskell Curry and his students, or by Robert Fies in Belgium. Curry and Fies, and Curry al. survey the early history of combinatory logic. For a more modern parallel treatment of combinatory logic and the Lambda calculus, see Barendug, who also reviews the models Dana Scott devised for combinatory logic in the 1960s and 1970s. Combinatory logic in computing. In computer science, combinatory logic is used as a simplified model of computation, used in computability theory and proof theory. Despite its simplicity, combinatory logic captures many essential features of computation. Combinatory logic can be viewed as a variant of the Lambda calculus, in which Lambda expressions are replaced by a limited set of combinators, primitive functions from which bound variables are absent. It is easy to transform Lambda expressions into combinator expressions, and combinator reduction is much simpler than Lambda reduction. Hence combinatory logic has been used to model some non-strict functional programming languages and hardware. The purest form of this view is the programming language Lambda, whose sole primitives are the S and K combinators augmented with character input/output. Although not a practical programming language, Lambda is of some theoretical interest. Combinatory logic can be given a variety of interpretations. Many early papers by Curry showed how to translate axiom sets for conventional logic into combinatory logic equations. Dana Scott in the 1960s and 1970s showed how to marry model theory and combinatory logic. Summary of the Lambda calculus. The Lambda calculus is concerned with objects called lambda terms, which can be represented by the following three forms of strings. V, where V is a variable name drawn from a predefined infinite set of variable names, and in a lambda terms. Terms of the form are called abstractions. The variable V is called the formal parameter of the abstraction, and is the body of the abstraction. The term represents the function which, applied to an argument, binds the formal parameter V to the argument and then computes the resulting value of, that is, it returns, with every occurrence of V replaced by the argument. Terms of the form are called applications. Applications model function invocation or execution. The function represented by is to be invoked with as its argument, and the result is computed. If is an abstraction, the term may be reduced. The argument may be substituted into the body of in place of the formal parameter of, and the result is a new lambda term which is equivalent to the old one. If a lambda term contains no subterms of the form, then it cannot be reduced, and is said to be in normal form. The expression E(v) equals of represents the result of taking the term E and replacing all free occurrences of E with A. Thus we write equals greater than E(v) equals of. By convention, we take as short for. The motivation for this definition of reduction is that it captures the essential behavior of all mathematical functions. For example, consider the function that computes the square of a number. We might write the square of x is x asterisk x. X here is the formal parameter of the function. To evaluate the square for a particular argument, say 3, we insert it into the definition in place of the formal parameter. The square of 3 is 3 asterisk 3. To evaluate the resulting expression 3 asterisk 3, we would have to resort to our knowledge of multiplication and the number 3. Since any computation is simply a composition of the evaluation of suitable functions on suitable primitive arguments, this simple substitution principle suffices to capture the essential mechanism of computation. Moreover, in the lambda calculus, notions such as 3 and asterisk can be represented without any need for externally defined primitive operators or constants. It is possible to identify terms in the lambda calculus, which, when suitably interpreted, behave like the number 3 and like the multiplication operator, Q(v). Church encoding. The lambda calculus is known to be computationally equivalent in power to many other plausible models for computation, that is, any calculation that can be accomplished in any of these other models can be expressed in the lambda calculus, and vice versa. According to the Church-Turing thesis, both models can express any possible computation. It is perhaps surprising that lambda calculus can represent any conceivable computation using only the simple notions of function abstraction in application based on simple textual substitution of terms for variables. But even more remarkable is that abstraction is not even required. Combinatory logic is a model of computation equivalent to the lambda calculus, but without abstraction. The advantage of this is that evaluating expressions in lambda calculus is quite complicated because the semantics of substitution must be specified with great care to avoid variable capture problems. In contrast, evaluating expressions in combinatory logic is much simpler, because there is no notion of substitution. Combinatory calculi. Since abstraction is the only way to manufacture functions in the lambda calculus, something must replace it in the combinatory calculus. Instead of abstraction, combinatory calculus provides a limited set of primitive functions out of which other functions may be built. Combinatory terms. A combinatory term has one of the following forms: x, p, where x is a variable, p is one of the primitive functions, and is the application of combinatory terms, and the primitive functions themselves are combinators, or functions that, when seen as lambda terms, contain no free variables. To shorten the notations, a general convention is that, or even, denotes the term. This is the same general convention as for multiple application in lambda calculus. Reduction in combinatory logic. In combinatory logic, each primitive combinator comes with a reduction rule of the form equals E, where E is a term mentioning only variables from the set x1, xn. It is in this way that primitive combinators behave as functions. Examples of combinators. The simplest example of a combinator is I, the identity combinator, defined by equals x for all terms x. Another simple combinator is K, which manufactures constant functions, is the function which, for any argument, returns x. So we say y equals x for all terms x and y, or, following the convention for multiple application, equals x. A third combinator is S, which is a generalized version of application. Equals S applies x to y after first substituting z into each of them. Or put another way, x is applied to y inside the environment z. Given S and K, I itself is unnecessary, since it can be built from the other two. X equals X for any term X. Note that although X equals for any X, itself is not equal to I, we say the terms are extensionally equal. Extensional equality captures the mathematical notion of the equality of functions, that two functions are equal if they always produce the same results for the same arguments. In contrast, the terms themselves, together with the reduction of primitive combinators, capture the notion of intensional equality of functions, that two functions are equal only if they have identical implementations up to the expansion of primitive combinators when these ones are applied to enough arguments. There are many ways to implement an identity function, and R among these ways is yet another. We will use the word equivalent to indicate extensional equality, reserving equal for identical combinatorial terms. A more interesting combinator is the fixed-point combinator or Y-combinator, which can be used to implement recursion. Completeness of the SK basis. It is perhaps astonishing that S and K can be composed to produce combinators that are extensionally equal to any lambda term, and therefore, by Church's thesis, to any computable function whatsoever. The proof is to present a transformation, T, which converts an arbitrary lambda term into an equivalent combinator. T may be defined as follows. T x equals greater than x. T equals greater than T lambda x e equals greater than T lambda x x equals greater than I. T lambda x lambda y e equals greater than T lambda x T lambda y e. T lambda x equals greater than. This process is also known as abstraction elimination. It is related to the process of bracket abstraction, which takes an expression E built from variables and application and produces a combinator expression x E in which the variable x is not free, such that x equals E holds. A very simple algorithm for bracket abstraction is defined by induction on the structure of expressions as follows. X, y equals ky, x equals I, x equals s. Bracket abstraction induces a translation from lambda terms to combinator expressions. By interpreting lambda abstractions using the bracket abstraction algorithm, conversion of a lambda term to an equivalent combinatorial term, for example, we will convert the lambda term lambda x, lambda y, to a combinator. T lambda x lambda y equals T lambda x T lambda y equals T lambda x 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 equals I. If we apply this combinator to any two terms x and y, it reduces as follows. I x y equals x I x y equals I x y equals I x y equals I x y equals y equals y equals the combinatory representation. I is much longer than the representation as a lambda term, lambda x, lambda y. This is typical. In general, the T construction may expand a lambda term of length n to a combinatorial term of length theta. Explanation of the T transformation. The T transformation is motivated by a desire to eliminate abstraction. Two special cases, rules 3 and 4, are trivial. Lambda x is clearly equivalent to I, and lambda x e is clearly equivalent to if x does not appear free in E. The first two rules are also simple. Variables convert to themselves, and applications, which are allowed in combinatory terms, are converted to combinators simply by converting the applicand and the argument to combinators. It is rules 5 and 6 that are of interest. Rule 5 simply says that to convert a complex abstraction to a combinator, we must first convert its body to a combinator, and then eliminate the abstraction. Rule 6 actually eliminates the abstraction. Lambda x is a function which takes an argument, say a, and substitutes it into the lambda term in place of x, yielding x equals a. But substituting a into in place of x is just the same as substituting it into both e and e. So x equals of by extensional equality, lambda x equals. Therefore, to find a combinator equivalent to lambda x, it is sufficient to find a combinator equivalent to, and evidently fits the bill, e, and each contain strictly fewer applications than. So the recursion must terminate in a lambda term with no applications at all, either a variable, or a term of the form lambda x, e. Simplifications of the transformation A to reduction. The combinators generated by the T transformation can be made smaller if we take into account the A to reduction rule. T lambda x equals T e lambda x is the function which takes an argument, x, and applies the function e to it. This is extensionally equal to the function e itself. It is therefore sufficient to convert e to combinatorial form. Taking this simplification into account, the example above becomes T lambda x lambda y equals T lambda x equals k. This combinator is equivalent to the earlier, longer one. Kxy equals xy equals y equals. Similarly, the original version of the T transformation transformed the identity function lambda f lambda x into I. With the A to reduction rule, lambda f lambda x is transformed into I. One-point basis. There are one-point bases from which every combinator can be composed extensionally equal to any lambda term. The simplest example of such a basis is x, where x lambda x, k. It is not difficult to verify that x equals eta beta k and x equals eta beta s. Since k, s, is a basis, it follows that x is a basis too. The IOTA programming language uses x as its sole combinator. Another simple example of a one-point basis is x lambda x, with x equals beta k and x equals beta s. X does not need eta contraction in order to produce k and s. In fact, there exist infinitely many such bases. Combinators B, C. In addition to S and K, Schönfinkel's paper included two combinators which are now called B and C, with the following reductions. He also explains how they in turn can be expressed using only S and K. These combinators are extremely useful when translating predicate logic or lambda calculus into combinator expressions. They were also used by Curry, and much later by David Turner, whose name has been associated with their computational use. Using them, we can extend the rules for the transformation as follows. T x equals greater than x. T equals greater than. T lambda x e equals greater than. T lambda x equals greater than I. T lambda x lambda y e equals greater than T lambda x T lambda y e. T lambda x equals greater than. T lambda x equals greater than. T lambda x equals greater than. Using B and C combinators, the transformation of lambda x lambda y looks like this. T lambda x lambda y equals T lambda x T lambda y equals T lambda x equals T lambda x equals C asterisk equals I, and indeed does reduce to equals. The motivation here is that B and C are limited versions of S, whereas S takes a value and substitutes it into both the applicand and its argument before performing the application. C performs the substitution only in the applicand, and B only in the argument. The modern names for the combinators come from Haskell Curry's doctoral thesis of 1930. In Schönfinkel's original paper, what we now call S, K, I, B and C were called S, C, I, Z, and T respectively. The reduction in combinator size that results from the new transformation rules can also be achieved without introducing B and C, as demonstrated in section 3.2 of CLK versus CLI calculus. A distinction must be made between the CLK as described in this article and the CLI calculus. The distinction corresponds to that between the lambda k and the lambda I calculus. Unlike the lambda k calculus, the lambda I calculus restricts abstractions to lambda x, E, where x has at least one free occurrence in E. As a consequence, combinator k is not present in the lambda I calculus nor in the CLI calculus. The constants of CLI are I, B, C and S, which form a basis from which all CLI terms can be composed. Every lambda I term can be converted into an equal CLI combinator according to rules similar to those presented above for the conversion of lambda k terms into CLK combinators. See Chapter 9 in Barendug. Reverse conversion. The conversion L from combinatorial terms to lambda terms is trivial. L I equals lambda x, x L k equals lambda x, lambda y, x L c equals lambda x, lambda y, lambda z. L b equals lambda x, lambda y, lambda z. L s equals lambda x, lambda y, lambda z. L equals. Note, however, that this transformation is not the inverse transformation of any of the versions of T that we have seen.